long, and you have a whole stack of questions to do towards the end of this lesson and also for homework. So guys, get to this page on resistance, please. Not sure what page it is. Page 12. All right. So we've covered a lot of ground in two lessons. In the first lesson, current, which is charge per time, number of electrons moving through a point. Then we looked at voltage, which was work done per unit charge. Then we got some equations for power, for energy, for current, for number of electrons. Okay. Now we're going to bring in the final variable that's involved in these in equations with energy and power and current and things like that. So, resistance. It's basically a measure of how much impedance there are, how much resistance there is to a flow of charge through a material, through a circuit, okay? So it's how a component reduces the electric current flowing through it, and it's measured in ohms. It was named after Georg Ohm. I believe he was Russian or German. But rather than capital O as the unit, we are using the Greek symbol omega. Okay? So it is named after another dude who measured resistance, but it's not capital. Well, it is capitalized because it's the Greek word for O. It's the capital omega. Now, before we get started, we have to have a source of pushing charges, something that's pushing electrons around the circuit. Otherwise, they would just spread themselves out nice and evenly. What we call it is an electromotive force, which is EMF, and it's sometimes simplified to a squiggly E. Now, this is often provided by, well, batteries is probably the simplest one. You can get solar panels. You can also get generators. Where can we write generator? Let me just move this omega out the way. Okay, so now I'm going to go back to, no I'm not. I'm going to draw my battery in first. So now here is a 9-volt battery. We would say that it provides an EMF of 9 volts. You could also say that the potential difference across the battery is 9 volts. You could say that every coulomb of charge that travels from that side to that side loses 9 joules. You could also say that each electron that passes from one side to the other loses 9 EV. Or if we want to convert it into joules, we times it by the fundamental charge, and it would be, what was it? 1.2 times 10 to the negative 18 joules. Okay, so there's so many ways that you could explain what this number means and what it represents. So, the battery provides an EMF of 9 volts. Let's just put him into a circuit. So I'm going to get a couple of wires. And then I'm going to, down here, I'm going to put a little sort of light bulb. Okay, so this is a very simple circuit. Now, let's figure out which way. Remember, the electrons are going to go from the negative. And remember, they've got lots of energy. And then when they get to here, there's a transfer of energy. Transfer. And then on this side, they've lost their energy and they return back. Obviously because the light bulb is converting out that electrical energy. So in this diagram, it's actually, I've run out of room. In this diagram, the globe is the resistance. That is the device that is impeding or stopping or reducing or resisting the flow of electrons. Okay, so that's our resistance. Now what we could do, we could get a special device called a voltmeter, and we could measure the voltage across the globe. Okay, so when we say voltage across, it would read 9 volts. It's basically saying that the potential difference is 9 volts. You're comparing the energy that the electron had on that side of the globe to the energy that the electron has on this side. It will have dropped by 9 volts. Okay? So you have to, when you're measuring the voltage of something, remember you're comparing from one point to another. Just like when you measure the gravitational potential energy of an object, you're comparing it from the ground to another point. So that you always need 2 points. So I could get my voltmeter and you literally place it across the globe. You can't just put it in one point because you've got nothing to compare with. Right? You've got to say, well, what's the difference in electrical potential on that side compared to that side? For this, it would be 9 volts. All right. Let's just get a little bit tricky with chemistry. The reason why we have this impedance is because the electrons have to jump across atoms. Okay? There's going to be atomic collisions. There's going to be electron collisions. Okay? These collisions are going to transfer energy. They're going to cause heat. Heat is the easiest transformation to understand. You're basically in your wire, as the electrons race across, they're going to start bashing and colliding into the electrons of the copper or tungsten filament and the atom and the nucleus, and they're going to start jiggling, and eventually they jiggle so much that they get really, really hot and they emit visible light. Okay? So that's where the energy transformation is occurring. If we were to look at the electrons can literally, in a metallic substance, they can jump across quite easily. So metals are good conductors, meaning they have a low resistance. And you guys would have covered this maybe in year 8 when you did electricity, or year 9 science. It's all about those valence electrons, okay? So here's your copper atom. And obviously you've got your electrons that are involved, but then you've got a couple of 2 spare floating around. Oh God, I'm committing myself to this horrible diagram. All right, so 27, wait, try again. 2 valence means 2, 8, 8, 16, what is it? 30?
32.
Whatever, there's 29. 27 of those electrons are locked in, and then there's 2 remaining floating around the outside. Those are the ones that could then jump across. All right, and if you're locked in a lattice, remember this is like a grid of atoms. So like frogs jumping along toadstools. Every time one electron jumps across, it's basically going to leave a vacancy in its wake that another electron jumps into. And as it's advancing onto the next atom, it literally pushes the atom in front of it. So if you move one electron on one side of the wire, you're literally moving billions of electrons because what happens is it's the electric field of that electron. As that field moves across, it creates a repulsive force on its neighbouring electrons. So it's this action at a distance. When you actually zoom in on at an atomic level, it's never in contact. There's no such thing as a contact. You never touch anything. Just the electrons on the outside of your finger is repelled by the electrons on the surface of the table. You never, if you zoom in, you're never actually touching anything. It's just you're getting to a point where the repulsion of the electrons on the surface of the table are repulsing and repelling the electrons on the surface of your fingers. Non-metals are poor conductors, and they generally have a high resistance. What are the exceptions? Can I spell exceptions? Yes, I can. Do we know the non-metals that can conduct electricity? It does have a C. God damn it. Lucky graphite is one. If you want to be fancy, we can have another allotrope of carbon, graphene. Okay. And so that's going to be... Oh. I'll take that away. So you look at the way that these guys are arranged in a, I don't know, covalent network arrangement. There are still electrons that are allowed to move around. So that's just a weird exception. All right, over the page. Let's keep cranking. Now, I want to get to how we explain resistance. If we were to plot voltage on the y-axis and then current, the flow of charge. Remember, voltage, this is going to be how much of a push there is to your charges. We could say the EMF, the electromotive force, we would get something like this. Well, zero EMF means that there's no pushing, there's no current flowing. But then you get, as you increase your voltage, you're going to get a perfectly linear proportion. It is linear. Calm down. It's not linear. It's linear. Get your rulers out. Oh, man. Come on, one note. Here we go. I should have just drawn a line and then put some dots on it. There we go. All right. So first thing, we get a linear relationship. Remember, that is your y equals mx plus c. All right. So we're going to play around with that equation in just a moment. So this could be a globe, this could be a wire, this could be a piece of metal, this could be a component in a circuit. If we double the EMF, we're doubling the force, the electromotive force. We're going to double the flow of charge. Increasing your EMF is like the school prefect at the canteen line going, all right, hurry up, stop mucking about, get in the damn canteen. If there's more force, you're going to get a greater flow of students through the canteen. Same here. If there's more force, there's going to be a greater flow of charge through your resistance. Okay? Now, what if I took a different substance that had a different physical property, different characteristics? Maybe they have a higher resistance or a lower resistance. So for the same voltage, maybe they get more current. So I'm going to now just draw a lower gradient for me, please. And try and keep your V values at the same height. Try your darndest. Because in a moment, I'm just going to sort of give a value for one of these dots. It does not matter. I've just decided to pick that second one up there. So, for the same amount of EMF, for the same amount of push in the circuit, if you get more current, then that would be a lower resistance. For the same amount of push, if you got less current, then that would be a higher resistance. And we will do an experiment where you essentially do this. You're going to vary the EMF across a device and you're going to measure the current that flows through it. Okay? It's pretty easy. You can just determine its electrical resistance. Now, there is no y-intercept. That equals 0 because have a think. As I said, if there's zero voltage or if there's zero EMF, then there's no force on your charges, they're not going to move. So with zero voltage or zero EMF, you would get zero current. And then it becomes a very, very nice y equals mx. Have a look here. I'm going to say V equals m times I. The gradient of this curve is the resistance. And we're going to call it R. R for resistance. So the equation now becomes, down here, we're going to call it Ohm's law. V equals IR. I'll draw that a bit nicely in just a moment. Let's get down here. Yeah, zoomed in, looks a little bit horrible. It's called Ohm's law. And it is V equals IR. Boom. Get that in a box and highlight it. And wouldn't you know it, it's in the data sheet as the other one. R equals V over I. Or we could express it one last way. I equals V over R. So there's three different ways to express Ohm's law. The one that's in the data sheet is this one. Okay. All right, so let's put this into application. If I said that I put 10 volts across of potential difference across a component, and for one, the red line, we got a flow of 2 amps. I'll just put the voltage at 10 volts, we get 2 amps. And then for the blue one, let's say we get 5 amps. We could measure the electrical resistance. So we would go R equals V on I equals 10 volts over 2 amps. That gives us 5 ohms of electrical resistance. For the blue component, we put the same 10 volts across it and we only got, we got more. We got 5 amps flowing across. That would give an electrical resistance of 2 ohms. Okay. No, we've established that you're not sorry.
Sorry, I didn't mean to convey offence. You said, I'm not sorry for doing it, I'm sorry for your reaction.
No, you're not.
I am.
Let's keep going, shall we? Now, this unit, we'll just stick with it's not a very, our brains don't really fathom it. Let's just go, what have we got? We've got, it's volts over amps, so it's joules per coulomb over coulombs per second, right? So that doesn't really simplify to anything nice. It's joules per coulomb squared per second. Let's just call it an ohm. All right, it doesn't really, you can't really visualize it. Like velocity, it's meters per second. Oh yeah, I can sort of visualize that. That doesn't really make much sense to us. The last statement that I'd like you to write is 1 ohm of resistance.
Excuse me, sir.
Yes?
Would it be per second? Because per second's on the bottom.
Oh, thank you. Seconds. It's even weirder. Joule seconds per coulomb squared. It's even weirder. It doesn't make any sense. 1 ohm of electrical resistance would allow 1 amp of current I mean, there's no real way to explain what 1 ohm is. If you applied 1 volt of potential difference across and you got 1 amp of current flowing through, that would be a resistance of 1 ohm. Okay? But basically, I'm just saying that, you know, R equals 1 over 1. 1 equals 1 over 1. Okay? Now, could I please ask you to skip this because we're going to do ohmic and non-ohmic next week. Let's skip resistivity. Skip chapter 5.4. Skip using multimeters, ammeter, voltmeter. let's get to the almighty trundle wheel of power, voltage, current, and resistance. Okay? Alright, now, this trundle wheel is not in the data sheet. Remember, I know we've written it quite a lot, but what we have in the data sheet is power equals IV and V equals IR. So we've got Ohm's law and the power equation. Okay. Now, Ohm's law is already there on our almighty trundle wheel. So if I said R equals V on I, that's Ohm's law. Tick, done. If I looked for V equals IR, there it is. There's Ohm's law. I equals V on R, there's Ohm's law there. If we look for the power equation, so let's just highlight him as... If we look for the power equation, P equals IV, there it is. Then we've got rearranging, V equals P on I, there we go. Going around, it's not present in I equals P on V, there it is. Yes. Huh? Yes, you do. Help him out. Cool. The other ones, and again, so we've got nearly all of the equations. What we can do to get the others is simply rearrange your power for one of the variables in ohm and then substitute it in. And you're going to get squares or square roots when you solve. So let's try one. Let's give it a red hot go. Let's say that V equals IR. So I could go P equals I bracket IR. So I've just substituted Ohm's law into the power law and we get I squared R. And is that on our trundle wheel? There he is, I squared R. We could rearrange that for R. R equals P on I squared. Do we have that on our trundle wheel? Yes, there he is. Last rearrangement, I equals the square root of P on R. Do we have that? Yes, we do. Okay. So that's just you substitute one equation into the other. Now, here's the thing. This trundle wheel is not in the data sheet. You're going to use it though to find the equation to solve for your unknown. But look what you've got. You've got 4 variables, and if you've been given 2, you can find the other 2 variables. In a test and an exam, you might just have to find the 3rd variable first in order to then find your 4th. You just have to do two steps, whereas the trundle wheel allows you to do 1 step. Okay? So, don't rely on the trundle wheel. Remember that, if you were given this in a test, you might just have to do a side mission to find the current first, and then you can use Ohm's law to find the resistance. But, for now, I would like you to use the above trundle wheel to find the unknown variables. So in each box, you're going to solve for one of the variables. I want you to pick the correct equation, substitute the values in, solve for the unknown. So this is cool now. All you need is 2 variables, and instantly you can find the other 4. Okay? So, again, you might find that you go one way with one equation, but your partner might choose the other equation and go a different way. You're going to get exactly the same values. So for example, I could go the weird way here and go, well, it's not the weird way. I'm going to solve for power first. I squared times R. Done. Okay? So please, pick the equation, substitute the values in. Do you want to get a drink, Hugo? Oh, you got one. All right. So now, guys, when you get to because now we've got 3 variables, there might be more than one way to solve for your 4th. So I would, again, pick the easiest one. You could go the square root of blah, blah, blah over blah, blah, blah. Or you could just go V equals IR. V equals IR is a little bit nicer. $30 volts. Okay? So, could you please solve the remaining questions for me? Go. Go. And have I given everything to 3 sig figs? I think I have. I have. So maybe I should be consistent with my sig figs. Okay. Hello.
This one.
Yeah, that was. It should have said I.
Okay.
That was my bad. You rubbing it in my face. I'm sorry. I'm sorry. I made a mistake. Wait, hang on. I'm not sorry. Not sorry.
You're just sorry for the effect.
No. All right. And then just be careful on, on the next page I've given some metric prefixes, so just be careful once you get to that second page. You've got orders of magnitude. Okay? All right.
This is annoying. You have to keep flipping
Would you guys like me? I'll freeze the trundle wheel on the board if you want. Alright, there you go. I'll stop the screen capture now.